Hello students. So here we are studying about the first category of nuclear reactions that release energy, that is nuclear fission. And as the name suggests, the nucleus of some heavy element will split into smaller nuclei in this phenomena. So basically nuclear fission is a reaction or a phenomena in which we can define it like that: a reaction in which a heavy nucleus, now a heavy nucleus refers to a nucleus having mass number even greater than 230, right? So quite heavy nucleus, when a reaction in which a heavy nucleus when excited splits into two smaller nuclei of about comparable masses, then such reaction is called nuclear fission. Nuclear fission is a phenomena or a reaction in which a heavy nucleus, when excited, it splits into two smaller nuclei of about comparable masses, then such phenomena is called nuclear fission. For example, if we take the example of uranium, so if we have a uranium nucleus and it is bombarded by slow moving neutrons, so uranium nucleus is 92 uranium 235, this isotope we are taking. So if we have a nucleus of 92 uranium 235 and it is bombarded by a slow moving neutron, by capturing this neutron it get excited and it splits into two nucleus, one of barium and one of krypton, and along with that it gives us three neutrons as a product with a release of energy. So barium is 56 141 and krypton is 36 92. So when uranium capture this slow moving neutron, it splits into barium and krypton along with the three neutrons and a release of energy. But later on, when detailed analysis was done on this particular combination, then we get that there are many more combinations possible. Means it is also possible that these two when react, or when this uranium nucleus capture this neutron, it give us xenon and strontium. Also it is possible that it give us cesium and lead as a product, as the fission nuclei. So there are many such combination possible. After this analysis, if we plot a graph between the fission yield percent and the mass number, then the curve that we got is, so the graph obtained is like this, and this shows that the most probable combination that we get is at these peaks. So this we get at A is equal to 95 and at A is equal to 140, which shows that the yield of this combination is maximum, and this shows that the out of all the combinations that we are getting, the two fragments of mass numbers 95 and 140 are present in high percentage. However, this dip shows that the chance of getting two fragments with exactly equal mass number is very small, right? Is extremely small, about 0.01%, right? It is about 0.01%. This shows that the two fragments that we are getting, those are of same mass. This is very rare. This percentage is very small. After that, this concept of nuclear fission or the theory of nuclear fission is explained on the basis of liquid drop model, in which the nucleus is assumed as a liquid drop of a spherical shape. Okay, so liquid drop model is used to explain the theory of nuclear fission that we are going to discuss here. In this model, we consider nucleus as a spherical liquid drop. This is the nucleus of uranium 235, right? And it is bombarded by neutron 0 and 1. So this is the spherical nucleus, which is equivalent to liquid drop of spherical shape. Now this is incompressible and has a uniform positive charge. The repulsion between the positively charged protons present in the nucleus, it tends to split the nucleus, but the forces of surface tension, the forces present because of the surface tension, as well as the short range nuclear forces that are present in between the nucleons of this nucleus, are trying to bind it or holding that nucleus or holding the nucleons together. Now when a nucleus capture a neutron, this is a new neutron that is captured by this nucleus, then the equilibrium gets disturbed. The equilibrium that was settled here in the nucleus, it get disturbed when it captured this slow moving neutron. The equilibrium get totally disturbed, and because of that its spherical shape due to excitation energy is changed, and the nucleus starts deforming into dumbbell shape structure. This spherical nucleus start deforming into dumbbell shaped nucleus into different stages. So it starts like this. First it gets some oval kind of structure, then it starts showing slight dumbbell, again this show clear dumbbells to us. So this is how it starts showing dumbbell kind of structure because of the large excitation energy and disturbance of equilibrium in that nucleus. And occasionally this led to the fission of this nucleus. So the oscillations that are happening inside the nucleus because of the capturing of this neutron, it led to the fission of nucleus at the end into two fragments along with the emission of three neutrons. So in the output we get two different segments. One is of barium, other is of krypton. Barium, krypton. Barium is 141, krypton is 92, along with three neutrons in the output. The nuclei of the fission products are also unstable, and these nuclei are also unstable when we obtain them, and they attain stability by emitting beta rays, gamma rays and more neutrons. So they get stable later on, but initially when they form they are also unstable. So that's how we explain the formation of two fragments in the process of nuclear fission. It happened because of the equilibrium disturbance that occur as soon as this slow moving neutron is captured by the nucleus of the uranium. Because of this capturing, the equilibrium inside the nucleus get disturbed, oscillations start setting up there, and because of those oscillations this spherical nucleus starts attaining dumbbell kind structure, and at the end it splits into two fragments actually, of different masses along with the three neutrons. So that's how the nuclear fission work. Now we can find the energy that we are getting during the reaction by a simple equation. So to get the energy Q, we have to find the mass defect in AMU. Okay, we have to find the mass defect in AMU, and this is our choice whether we are using the energy relation E is equal to mc square. That means if we multiply it by c square we get the answer for the energy, but it won't be in electron volt term, right? It will be in joules. If you are using delta m in kilograms and c square in meter per second in SI system, then we get the answer in joules. But if we are using delta m in atomic mass unit, that we actually do practically, so by multiplying this value just by 931, because we know that 1 AMU is equivalent to 931 MeV of energy. So if we are getting delta m AMU mass defect, that means if we multiply this into 931, we get the answer of energy in million electron volts. So that much energy is released during the reaction. So we can find the energy released during a nuclear fission reaction by just finding the mass defect in AMU. When you find the mass defect in AMU, after getting this, multiply it by 931, the answer we get will be the energy released in million electron volts, that is MeV, because 1 AMU is equal to 931 MeV. So that's all about the nuclear fission. For the video of nuclear fusion, stay tuned and keep studying. Thank you.